Tonight we are going to explore one of the most unsettling facts in all of astronomy. Our telescopes reach 46 billion light-years in every direction. Hundreds of billions of galaxies sit inside that sphere. We've measured their distances. We've measured what they're made of. We've photographed the light of galaxies that formed less than 300 million years after the Big Bang. Every one of them is out there right now, shining. But most of them are already gone. Not gone from view, gone from reach. Fire a beam of light at them tonight at 186,000 miles a second and it never arrives. Not in a billion years. Not ever. 94% of what we can see, we can never touch. And by the end of tonight, you're going to understand exactly where that line sits and why the light still reaches us from the far side of it. If you find this kind of thing as strange and as beautiful as I do, take a moment to subscribe and leave a like. It's a small thing and it helps this channel find the other people who look up. And tell us in the comments what city you're listening from and, if you don't mind, what time it is where you are. Tonight is a video about arrival times, about signals that make it and signals that don't. It's good to know that this one arrived. Now, let's begin. Let's start with something you can see with your own eyes. On a dark night in autumn, in the northern half of the world, look toward the constellations Andromeda and Cassiopeia. There's a patch of sky between them that doesn't look like much. If you know roughly where to aim, you'll find a small gray smudge, slightly fuzzy, slightly oval. Easy to mistake for a star that's out of focus or for a smear on your glasses. Most people who see it don't notice they've seen it. That smudge is the Andromeda galaxy. It's a spiral of roughly 1 trillion stars and it's wider than our own. And it sits 2.5 million light-years away. That's the farthest thing a human eye can reach without help. There's an asterisk on that one. The Triangulum galaxy sits a little farther out, at close to 3 million light-years. Very sharp eyes can pick it up under very dark skies. But for almost everyone, on almost every night, Andromeda is the edge of unaided human vision. We only worked out what it is fairly recently. For most of human history, that smudge was filed away as a nebula, a patch of glowing gas somewhere inside our own galaxy, because our own galaxy was assumed to be the whole universe. Then, in the early 1920s, Edwin Hubble found a particular kind of pulsing star inside it. He used the rhythm of the pulse to get a distance. The answer put it far outside the Milky Way. It wasn't a cloud in our neighborhood, it was another galaxy, comparable to our own, and there were going to be more of them. The universe got much larger in about a year, and it hasn't stopped since. Keep that name in mind. We'll need it again shortly. 2.5 million light-years is a number that slides straight off the mind, so let's put a floor under it. 1 light-year is about 5.88 trillion miles. That's the distance light covers in a year, moving at 186,000 miles every second. No pausing, no slowing, no shortcuts. Now take that distance and lay it end to end 2.5 million times. That's the gap between us and the faint gray oval you can see tonight with nothing but your own 2 eyes. Here's the part worth sitting with. Nothing moves faster than light. And even at that speed, the light hitting the back of your eye tonight left Andromeda about 2.5 million years ago. Our species is around 300,000 years old, so that light was already most of the way here before there was anyone to see it. It set out when the first members of our genus were chipping flakes of pebbles in East Africa. Every stone tool since then. Every migration. Every language, every city, every war, every song ever written. All of it happened while that light was still in transit. It crossed the gap between 2 galaxies and the entire human story fit comfortably inside the trip. So you aren't looking at Andromeda, you're looking at a photograph of Andromeda, taken 2.5 million years ago and delivered tonight. And this is true of everything up there at every scale. The moon is about 1 second and a third away. When you look at it, you're seeing it as it was while you were finishing your last blink. The sun is 93 million miles out, which comes to 8 minutes and change. If it went out right now, we'd have 8 ordinary minutes before anything on Earth noticed. The bright stars of winter are years away. The far side of our own galaxy is tens of thousands of years away. There is no such thing as looking at the sky and seeing the present. Not as it is, never as it is. Every point of light up there is a report. And every report is old. And the farther away the source, the older the report gets. Astronomy isn't observation of the universe. It's the reading of mail that's been in the post for a very long time. Most of the time, this is a charming fact. It's the kind of thing people say at parties, but it stops being charming the moment you ask the obvious follow-up, which happens to be the question this entire video turns on. If we're always seeing the past, then what is the picture actually showing? What's the relationship between the thing in the frame and the thing that's out there tonight? Hold on to that. We'll come back to it with everything we've got. Now, let's talk about what happens when we stop looking with our eyes and start collecting with a camera. The delay is already 2.5 million years for the nearest big galaxy, which makes a deep photograph of empty sky a much stranger object than it looks. The year is 2003. The director of the Space Telescope Science Institute has a small allotment of Hubble time he can spend however he likes. It's called discretionary time, and it exists so that somebody can take a risk that a committee would never approve. Stephen Beckwith decides to spend a large slice of his on nothing. That's the actual plan. Point the most valuable telescope humanity owns at a piece of sky that contains nothing and leave it there. The target sits in the southern constellation Fornax. It's picked precisely because it's empty. No bright stars in the way, no nearby galaxies, very little dust from our own galaxy hanging in the line of sight. It's a clean window, and it's small, about a tenth as wide as the full moon. 11 square arc-minutes of sky, which is a patch you could hide behind a grain of sand held out at arm's length. Hubble is the most oversubscribed instrument in the history of science. Astronomers write proposals for years and get turned down. Careers hang on a few hours of it. And the plan is to spend 11 days of that time on a blank spot. The observations run from the 24th of September 2003 to the 16th of January 2004. Hubble takes about 800 separate exposures across 400 orbits of the Earth, each one running roughly 20 minutes. The total comes to just under 1,000,000 seconds of open shutter, 11.3 days of continuous staring at nothing. Mechanically, that's harder than it sounds. The telescope is moving. The Earth is moving. Every 90-odd minutes, Hubble swings around the planet, loses the target behind the Earth, and has to find it again. 400 times. And every one of those exposures has to be stacked on top of the others with the precision of a rifle shot. Otherwise, the whole thing smears into gray. Then the image comes out. 10,000 galaxies. Not 10,000 stars. 10,000 galaxies, each one a city of 100 billion suns. All of it packed into a patch of sky you could cover with a grain of sand. Spirals, ellipticals, little red smears that are barely galaxies yet, caught in the act of assembling. Some of them look like nothing we have names for. And the emptiness was never real. It was a limit of the equipment. There was never a blank spot in the sky. There is no blank spot in the sky. Every direction you can point is like this. Pick a random patch of darkness above your head right now, anywhere. Behind it, there are 10,000 galaxies waiting for a long enough exposure. To photograph the entire sky at that depth, Hubble would need about 1,000,000 years of continuous observing. We have imaged a rounding error of the available universe, and the rounding error contained 10,000 galaxies. That image changed what people thought the word universe referred to. It's on posters and textbook covers and the walls of planetariums. It is probably the single most reproduced photograph in the history of astronomy. And it's also the beginning of the bad news, though nobody framed it that way at the time. Because we don't just have the picture, we have the distances. Astronomers went back to that same patch with spectrographs, which split the light from each smear into its separate colors. Inside those colors sit the fingerprints of hydrogen and oxygen and carbon, at wavelengths we've measured in laboratories for well over a century. Find the fingerprint, see how far it's been shifted from where it belongs, and you have a distance. It's slow work, one faint object at a time, and it's been going on ever since. And the answers break ordinary arithmetic in a way that takes some care to unpack. So let's talk about how far we can see, not how far we'd like to, how far the physics allows. Start with the simple version, the one that feels like it has to be right. The universe is 13.8 billion years old. Light travels 1 light year in 1 year. Nothing beats it. So the farthest anything can possibly be, if its light has reached us, is 13.8 billion light years away. That's the whole calculation. It takes 4 seconds and it uses nothing but a stopwatch. It's also wrong. The actual figure is 46.5 billion light-years in every direction, 93 billion light-years across. That's not a small correction. That's more than 3 times the number the stopwatch gives you, and it isn't a measurement error. And it isn't a disagreement between rival groups. It's the accepted answer, and it's been the accepted answer for decades. And if you sit with it for a moment, it should feel impossible. How does light travel 46 billion light-years in 13 billion years? The answer is that the photon never broke the speed limit. The road got longer while it was on it. The mechanism goes like this, and we'll take it slowly, because everything else tonight sits on top of it. Space isn't a stage that things move around on. It's a participant. It has a size, and that size increases, not into anything. There's no outside for it to expand into. The distance between any 2 points that aren't held together by gravity simply grows. So picture a photon leaving a galaxy 10 billion years ago, aimed at the spot where the Milky Way will eventually be. It covers a light year every year, faithfully, without a single deviation. But while it's in flight, new space is appearing between it and its destination. It closes the gap reopens. It closes it again, it reopens again. It gets there. It just gets there, having crossed a distance that no longer matches the time it took. The same stretching happens to the wave itself. A photon is a wave, and if the space it's traveling through gets bigger, the wave gets bigger too. It leaves the galaxy as blue light. It arrives as red light, or as infrared, or as microwaves. That's what redshift is. It isn't the sound of an ambulance driving away from you. Nothing is driving anywhere. The wave grew because the room grew, which means redshift is a ruler. Measure how far the wave has been stretched, and you know how much the universe expanded during the trip. That's the whole trick. It's how we date every distant object. And it leads to the strangest consequence of all. The most distant light we receive was, for the first stretch of its journey, actually losing ground. Space was opening between the photon and us faster than the photon could close it. It was pointed straight at us, moving at the speed of light, and getting farther away. It was traveling toward us and receding from us at the same time. Then the expansion rate dropped enough that the photon started making headway. After billions of years of effort, it crossed the last of the gap and landed in a detector. The light in the deepest images we own has been outbound longer than the Earth has existed. And it spent part of that trip going backwards in the only sense that matters. But this raises another question. If space is carrying things away from us, how fast is it carrying them? The rule was worked out in 1929, and it's disarmingly simple. The farther away a galaxy is, the faster it recedes. And the relationship is straight. Twice the distance, twice the speed. 10 times the distance, 10 times the speed. The constant of proportionality is where things get concrete. For every 3.25 million light-years of distance, a galaxy pulls away from us at somewhere between 42 and 46 miles a second. In metric, that's about 67 to 73 kilometers per second per megaparsec. And a megaparsec is that 3.25 million light-year unit. One thing about that rule before we start pushing on it, it doesn't point anywhere. You might assume that if everything is running away from us, then we are sitting at the center of the retreat. We are not. Take the same measurement from a galaxy on the far side of the observable universe and you get an identical result. Everything receding, faster with distance, in every direction. There's no location the expansion is running away from, because nothing is running. Every observer in the universe sits at the center of their own recession, and not one of those centers is the real one. Now sit with the shape of the rule, because it has no breaks in it. Nothing in the equation caps the answer. It's a multiplication. Take a galaxy far enough away and multiply. The recession speed passes 42 miles a second, then 400, then 4,000. Eventually, it passes 186,000 miles a second. That's the speed of light. The distance where that happens is about 14.3 billion light-years. Astronomers call the sphere at that radius the Hubble sphere. Every galaxy outside it is receding from us faster than light, and we have catalogued hundreds of them. We photograph them routinely. There are dozens in that 11-day exposure. That sentence tends to stop people, because it sounds like a violation of the one rule everyone knows. It isn't, and the reason matters. Nothing is moving through space faster than light. Those galaxies are sitting still in their own neighborhoods, orbiting their own companions, doing nothing unusual. It's the space between us that's growing, and the growth of space has no speed limit attached to it, because it isn't a speed. Nothing is traveling. There's just more room than there was. Which raises the obvious problem. If a galaxy is receding faster than light, how does its light ever reach us? Picture a swimmer in a river. The current runs downstream faster than she can swim upstream, so she loses ground. Every stroke, she ends up farther from the bank she's aiming for. By ordinary logic, she never arrives. But this particular river slows down as you move toward the middle, and she's drifting toward the middle. So the current weakens under her, stroke by stroke, until there's a moment when her swimming finally beats the flow. From then on she gains, slowly, then steadily, then she's at the bank. That's what the photons are doing. The Hubble sphere isn't fixed. It has grown over cosmic time and it keeps sweeping outward. A photon emitted from beyond it loses ground at first, sometimes for billions of years. Then the sphere overtakes it and it finds itself inside. From there it can make progress. So the galaxy you're looking at is receding faster than light and always has been, and you can still see it. It sent the message from the wrong side of the line and the line moved. Now think about what that means for you sitting there. Some of the light landing on a telescope mirror tonight comes from objects that should never have reached us at all. Not under any straightforward reading of the rules. They got a reprieve. A slowdown in the expansion gave their light a window, and the light took it. Which is fine, as long as the expansion keeps slowing down. For most of the 20th century, nobody seriously doubted that it did. The universe is full of matter. Matter pulls on matter. The expansion started fast, and gravity has been fighting it ever since. So the expansion has to be losing speed. That wasn't a fringe position. That was the entire field. The only open question was whether gravity would win outright and pull everything back together, or whether the universe would coast forever, slowing but never stopping. Two numbers would settle it. How fast is the universe expanding now, and how much has that rate dropped? Measure both, and you know how the story ends. We need to talk about 1998. Two teams are racing to make that measurement, and they don't like each other much. One is the Supernova Cosmology Project, based in Berkeley, run by Saul Perlmutter, grinding away since the late 80s. The other is the High-Z Supernova Search Team, put together in 1994 by Brian Schmidt. A young researcher named Adam Rees leads the analysis. Same goal, same method, different data. The method depends on a very particular kind of explosion. A white dwarf is the burned-out core of a dead star. It's about the size of the Earth, and it carries roughly the mass of the Sun. That makes it one of the densest things in the sky. If it has a companion star close enough, it steals gas from it. Slowly, over a long time, it puts on weight, and when it crosses a certain threshold, it detonates. The important part is the threshold. Because the trigger is always the same, the explosion is always about the same brightness. Every one of them, anywhere in the universe, peaks at nearly the same true luminosity, bright enough to briefly outshine an entire galaxy, which turns them into rulers. If you know how bright a thing really is and you measure how bright it looks, the difference tells you how far away it is. Dimmer means farther. That's the whole logic, and it's the closest thing astronomy has to a tape measure that reaches across the universe. So both teams go hunting. They find supernovae halfway back to the beginning. They measure how bright each one looks and how much its light has been stretched. They plot brightness against redshift. Then they wait for the curve to bend the way gravity says it must. In a universe that's been slowing down, distant supernovae should look a little brighter than a coasting universe would predict. Deceleration keeps them closer than they'd otherwise be. That's the prediction. That's what everyone is expecting to see in both camps. Each side has spent the better part of a decade building the machinery to see it. The distant supernovae come back about a quarter dimmer than expected. Dimmer means farther. Farther than a decelerating universe allows. Farther than a coasting universe allows. Farther than anything in the standard picture permits. Both teams assume they've made a mistake, and they go looking for it. This is the part of the story that's hardest to imagine living through. Dust in the way would dim them, so they test for dust. Supernovae in the early universe might have been intrinsically different. so they test for that. Bad calibration, bad photometry, selection effects that favor the brightest examples at long range. They test all of it. Months of trying to kill the wrong result. It doesn't die. The expansion isn't slowing. It's speeding up. Take a second with that. Nothing ordered it. No theory demanded it. Nothing in the inventory of the universe, as understood in 1997, could push outward. Gravity pulls. That's the only thing gravity does. Both teams publish separately, within months of each other. The rival results agree, which is the only reason anyone believes either of them. Michael Turner gives the unknown cause a name: dark energy. It's a label attached to an absence. It says that something is making space expand faster. It says nothing whatsoever about what that something is. More than a quarter of a century later, it still says nothing. Whatever it is, it accounts for around 70% of everything there is. Perlmutter, Schmidt and Rees shared the Nobel Prize in Physics in 2011. And this is the moment the sky changed meaning, though almost nobody outside the field noticed at the time. Because if the expansion is accelerating, then the swimmer in the river doesn't get her reprieve. The current doesn't weaken, it builds. And the arithmetic of who can ever reach whom changes completely. Now, let's talk about what acceleration does to a map. Take the observable universe, that sphere reaching 46.5 billion light-years in every direction. Sort everything in it by whether we could ever get there. Not with our current engines. Ever with anything, up to and including a beam of light fired tonight. 4 categories come out, and the boundaries between them are hard. Zone 1. Everything closer than about 18 billion light-years. We can see it, and we can reach it. Send a signal tonight, and it lands. Send a ship, and given enough centuries, the ship arrives. This is the part of the universe we are still connected to in the future tense. Zone 2. Everything between 18 and 46 billion light-years. We can see it, and we will always be able to see it, and we can never reach it. Not with a ship, not with a radio signal, not with a photon fired right now at the full speed of light, tonight, with perfect aim. It leaves, and it never lands. Zone 3. Everything between 46 and 61 billion light-years. We can't see it yet. Its light left long ago and is still crossing the gap, and one day it will arrive. New galaxies will surface in our images. We'll be able to look at them and never touch them. Zone 4. Everything past 61 billion light-years. Nothing. No light, no signal, no contact in either direction for the entire future of the universe. Zone 3 is the one people find hardest to believe, so it's worth stopping on. There are galaxies out there whose light has been in flight since nearly the beginning and still hasn't landed. It will. Over the coming ages, objects nobody has ever seen will surface in our images for the first time. Every one of them will arrive already out of reach. The sky is going to gain members. Our reach is not. And none of this is about us specifically. That 18 billion light-year sphere isn't a property of Earth or of the Milky Way or of any particular address. Every galaxy in the universe sits at the center of one, drawn around itself with the same radius, which makes the relationship mutual. A galaxy 30 billion light-years from here is outside our sphere, and we are outside theirs. Their old light reaches us. Our old light reaches them. Neither of us can ever answer. Zone 2 is the hinge of the whole night, and the mechanism behind it goes like this. While the expansion was slowing, every object was eventually reachable. A photon might lose ground for a while, but the current always weakened, and given enough patience, it always got there. Nothing was permanently out of bounds. The universe was large and slow, and in principle, fully connected. Acceleration removes the patience clause. The gap between us and the distant galaxy now widens faster every year. A photon aimed at it loses ground, and next year it loses more ground, and the year after that, more still. There's no crossover coming. The current never weakens. The photon flies forever at the speed of light, and the distance to its target increases forever, and the two curves never meet. That's what a cosmic event horizon is. Not a wall, Not a boundary you'd notice if you flew up to it, just a distance past which no message we send tonight will ever be delivered. Now, the number that does the real damage. It comes out of geometry, not out of cosmology. 18 billion light-years out of 46 billion is about 39%, roughly 2/5 of the way to the edge. Stated that way, it doesn't sound catastrophic. It sounds like we own a solid chunk of the place. Most people hearing that figure would guess we've lost about half the universe and kept the rest. But the sky isn't a line, it's a volume, and volume scales as the cube of the radius. Take a ball and shrink its radius to 39% of what it was. You haven't kept 39% of the contents, you've kept 39% multiplied by itself 3 times, which comes to about 6%. 6%. Roughly 1 part in 16. 19 out of every 20 galaxies in our catalogs sit on the wrong side of the line. Every deep image we've ever taken is mostly a photograph of places that are already permanently out of bounds. And notice what's not happening. They haven't gone anywhere. They aren't fading. They aren't hiding. They're right there, in the data, sharp and bright and thoroughly measured. We know their distances. We know their masses. We know which elements are burning in their stars and roughly when those stars ignited. We have their coordinates written down to a precision that would let a navigator plot a course tonight. We can see them. We can photograph them. We can weigh them, date them, and name the elements inside them. We can't go. Look up at a clear sky, and you're seeing 100% of the picture and 6% of the property. The view is complete. The access is not. And nothing in the appearance of the sky tells you which is which. The light from the unreachable side looks exactly like the light from ours. It's the same photons. It arrives in the same instruments. There's no marker on it. So which ones exactly are on the far side of that line? The formal answer is a redshift of about 1.7. Past that, unreachable. That's precise, and it's useless to anyone standing outside with a telescope, because you can't eyeball a redshift. So here's a version you can actually carry around. If the light in the image has been flying for more than about 10 billion years, that galaxy is already gone. That's the rule. It's approximate, and it moves a little depending on which measurement of the expansion rate you trust. But as a working line, it holds. Light that's been on the road 7 or 8 billion years is from a galaxy we could still send something to. Light that's been on the road 11 or 12 billion years is from a place we could never touch. Under any circumstances, with any technology, in any future. 10 billion years of travel. That's where the door closed. And once you have that rule in your hand, go back through the famous pictures and start sorting. Take the most extreme case we currently have. The galaxy is called MOM-Z14, confirmed by the James Webb Space Telescope, and its redshift is 14.44. Nothing further has been confirmed. We see it as it was 280 million years after the Big Bang. That's early enough that it shouldn't look the way it does. It's small, a couple of hundred light-years across, next to about 100,000 for the Milky Way, and it's far brighter than the models said anything at that age could possibly be. Its light has been traveling for roughly 13.5 billion years. Tonight, that galaxy sits about 33.8 billion light-years away, which is nearly twice the reach line. Not a near miss, not a difficult case. It's almost twice as far past the line as the line is from us. Every photon we've ever collected from it is a message from a place that has never been connected to us, and never will be, in any direction that matters. And that's the frontier object, the one that makes headlines. Run the same test across that 11-day exposure. Most of the galaxies with measured distances in the most famous photograph in astronomy fail it too. Let's consider the cruise position, because one more number is attached to all this, and it's the harder of the two. A trip out to the edge of the reachable zone isn't the absurd proposition it sounds like. Take a ship holding a steady 1 gravity of acceleration, the same pool you're sitting in right now. It would spend about 100 years of shipboard time getting most of the way there. 100 years is a long life. It isn't an impossible one. Relativity is generous in a way people rarely appreciate. At high enough speed, the clock on board slows. Distances that take billions of years in our reckoning compress into something a crew could live through. So the one-way trip is on the table. Physically permitted, wildly beyond us, but on the table. The round trip is not. Go out and come home, and the maximum reach collapses from a redshift of 1.7 to a redshift of 0.65. That's the number to hold on to tonight. Less than half. And because volume scales as the cube, the zone you can visit and return from is a small fraction of the zone you can visit. Now put a crew inside those numbers. A crew leaves for the far edge of the one-way zone. They accelerate for decades. They arrive somewhere out past everything, at a galaxy that formed 9 or 10 billion years before they were born. They can land, they can build, they can look around at a place no one from Earth will ever see any other way. And they cannot come back. Not slowly, not eventually, not with better engines or more fuel or more time. And they cannot tell anyone what they found. A signal aimed home has to cross a gap that's widening the whole time it's in flight. That isn't a matter of building a stronger transmitter. It isn't a power problem at all. The signal leaves at the speed of light, which is the fastest anything leaves. And the road behind them lengthens faster than the signal can shorten it. They could aim a beam back at the sun and hold it there for the rest of the universe's existence. It would still be outbound, still traveling, still arriving nowhere. So what do you do with a destination you can reach but never report from? Who signs off on a mission whose findings no one will read? What is a discovery that can't be sent home? What would you put on the ship, knowing that nothing at all is coming back the other way? Nobody has answers to those. We've barely started asking them. And there's something in those two numbers that nobody has explained. The one-way line sits at a redshift of 1.7. The round trip line sits at 0.65. The engine is the same engine. The crew is the same crew. The fuel is the same fuel. And the physics of the rocket doesn't change between the outbound leg and the return. Nothing about the machine accounts for the difference. The asymmetry isn't in the ship, it's in the road. So let's look at what the road is doing, because every number from here forward is built on top of it. We still don't know what dark energy is. That hasn't changed, and it isn't going to change tonight. But we know how it behaves, and we know it in detail, and the behavior is stranger than the mystery. Start with the two ordinary ingredients. Matter is the easy one. There's a fixed amount of it in any patch of the universe, and the patch keeps getting bigger, so the matter inside gets thinner. Stir a spoonful of sugar into a glass of water, then pour that into a pitcher, then into a bathtub. The sugar hasn't gone anywhere, there's just more water around it every time you look. Radiation is the same, only worse. Light thins out as the volume grows, exactly like the sugar. But each individual photon also gets stretched as it travels, which drains energy from it. So radiation loses on two fronts at once. In the first 50,000 years after the beginning, radiation ran the whole show. Now it's a rounding error. Dark energy does neither of those things. Its density stays flat, not roughly flat, flat. Double the volume of the universe and you have twice as much dark energy in it, at exactly the same concentration as before. New space shows up already carrying its own supply. That last part has no everyday parallel at all. Imagine building an extension onto your house and finding the new rooms already furnished, out of nowhere, at the same density as the old ones, every time, forever. That is not how anything you have ever owned behaves. You might reasonably ask how anyone could know that. The answer is in the shape of the expansion history. Different ingredients bend that history in different ways. Matter bends it one way, radiation bends it another. A component whose density never drops bends it a third way. And the three curves don't look alike. We have thousands of supernovae now, spread across billions of years of look-back time. We have the microwave background. We have the clustering pattern of galaxies across the sky. Lay all three of those against each other, and only a narrow family of curves survives. The curve that survives is the flat one. Physicists compress that into a single number. The measured value has sat within a few percent of the flat density case through every improvement in the data for 25 years. There's a second thing that flat density does, and it's easy to miss. In a decelerating universe, pick any galaxy and watch it for long enough, and its recession speed drops. In ours, it climbs. The same galaxy pulls away faster and faster with no force acting on it and without moving through space at all. And it sets up a race with a guaranteed winner. Early on, matter was thick and dark energy was a whisper underneath it. Gravity was pulling on a crowded universe and the expansion slowed, year after year, exactly as everyone expected. But matter kept thinning. Dark energy didn't. So the ratio between them shifted, slowly, for billions of years, in one direction only. The crossover happened when the universe was about 7.8 billion years old. That's roughly 6 billion years ago. Put the whole history of the universe on the face of a clock, starting at midnight. The switch flips a little after 1:30 in the afternoon, and the rest of the day belongs to dark energy. Before that moment, every distant galaxy was receding a little more slowly each year. After it, every galaxy not held down by gravity started receding a little faster each year. Nothing about the galaxies changed. The balance of the ingredients changed underneath them. Today, dark energy is roughly 70% of everything there is. And here's where it lands on you personally. There has never been a human being who lived in the decelerating universe. Not one. The switch flipped before the Earth existed. Every star you have ever looked at, you looked at through accelerating space. The version of the universe where patience eventually gets you everywhere ended long before there was anyone around to be patient. That crossover did something else, and it doesn't get advertised. For the first 8 billion years, the universe was in the business of building things. Gravity pulled small clumps into bigger clumps. Bigger clumps became galaxies. Galaxies fell together into groups. Groups fell into clusters. Clusters were drifting toward each other, and if you'd extrapolated from that, you'd have predicted structures that kept growing without end. That process is over. Anything that wasn't already gravitationally bound at the crossover is never going to become bound. The pieces are moving apart faster than they can pull each other in, and the gap widens every year. Construction has stopped. What we have now is the finished inventory, which turns some very famous objects into something other than objects. In 2014, a team mapped the flows of galaxies around us and named the region we sit in Laniakea. It's about 520 million light-years across and contains something like 100,000 galaxies. It has a shape, a center of mass, and a beautiful map that has been on posters ever since. Put the local group on your kitchen table as a dinner plate. On the same scale, Laniakea is a circle 100 times wider, drawn out past the far end of the yard. But Laniakea is not held together. It never was. It's a pattern in the motion of things that are already leaving. Each of its component groups and clusters is bound to itself and to nothing larger. Dark energy is pulling them apart right now, and it has been doing it for longer than the Earth has existed. The same is true of every supercluster in every diagram you have ever seen. They're real in the sense that a crowd is real. Photograph a crowd at the exact moment it starts to disperse, and the photograph still looks like a crowd. So what's actually ours? The Virgo cluster is bound. It sits about 55 million light-years away and holds well over 1,000 galaxies. Our own group has a few dozen. A giant elliptical called M87 anchors the middle. The light in tonight's image of Virgo left about 10 million years after the last dinosaur died. That cluster will hold together for as long as there's anything to hold. But it's bound to itself. It isn't bound to us. What's bound to us is the local group. Roughly 5 million light-years across, several dozen galaxies, most of them small and dim, with the Milky Way and Andromeda as the two large ones. That collection has decoupled from the expansion entirely. Space can stretch as much as it likes, and the local group will not stretch with it. That word, decoupled, deserves a moment. Because most people assume the expansion is happening everywhere, including inside them. It isn't. Your body isn't expanding. Your chair isn't expanding. The Earth's orbit isn't drifting outward. The solar system isn't inflating, and the Milky Way isn't getting wider. Anywhere that gravity, or chemistry, or the forces holding atoms together are in charge, the stretching loses outright. It isn't a close contest. Expansion only wins in the empty places between the bound things. That's the entire geography of tonight. Islands that hold, and a widening gap between them. That's the estate. Everything else on the map is a tenant whose lease has already run out. On that scale, the map isn't scattered dots. Matter is strung along filaments, thin, bright threads of galaxies running for hundreds of millions of light years. Where the threads cross, you get clusters. Between them are voids, vast and nearly empty, with almost nothing inside them at all.
Gravity assembled that whole arrangement over billions of years out of faint ripples in the early universe.
It's the largest pattern in existence. It's also the last one there's ever going to be. And we're moving through it. Measured against the ancient background light, the entire local group is traveling at roughly 400 miles a second. It's being pulled toward a great concentration of mass, off in the direction of Centaurus. That's not the expansion. That's an actual fall, under actual gravity, in an actual direction. We are never going to arrive. The thing pulling on us is receding faster than we are falling toward it, and the gap is widening every year. We are in free fall toward a destination that's already unreachable. We have been for the whole of human history, and nothing in the motion gives it away. So the expectation was structures growing without limit. The measurement is that the largest bound things that will ever exist finished forming a few billion years ago. The cosmic web isn't a work in progress, it's a final draft. Every map of large-scale structure ever published, including the ones being made this year, is a photograph of something dissolving. That's not a metaphor, that's the caption. And the same clock is running on our reach. Here are the raw figures, and they're worth having in front of you. The observable universe holds something like 2 sextillion stars. Of those, the ones we could still reach if we left tonight at the speed of light, number about 120 quintillion, 6 in every 100. Out of 100 stars in the sky, 6 are ours. The other 94 are decoration. Now, let it run. A billion years from now, 6% has fallen to 5. About 20 quintillion stars cross the line in that stretch, which is 1 out of every 6 we can currently reach. And the line itself retreats from about 18 billion light-years to about 16.7.
A billion years is long enough for a whole new kind of animal to appear on this planet, spread across it, and go extinct, several times over. In that same window, the line comes in by more than a billion light-years. Keep going. About 6 billion years out, the reachable share drops below 2%. 35 quintillion stars left. By then, the sun has swollen into a red giant, and the surface of the Earth is a memory. Around 63 billion years, everything reachable fits inside what's left of our own supercluster. Just before the 100 billion year mark, the Virgo cluster crosses the line. All of it, gone from reach in a single stretch. And past 110 billion years, the last group goes. It's a cluster near the Big Dipper called the M81 group, our closest neighbors outside the local group. They'll be the last things out the door. 112 billion years is about 8 times the current age of everything. In a billion years, 5%. In 6 billion, under 2. In 63 billion, 1 supercluster's wreckage. In 100 billion, no Virgo. In 112 billion, nothing at all outside our own front door. And none of it happens in leaps. It's continuous. Every year, a thin shell of space crosses from the reachable side to the other one. It carries off whatever stars happened to be sitting inside it. There's no announcement. No instrument registers anything at the moment it occurs, which is part of what makes the whole business so hard to take seriously. One version of this lands harder than the rest. If you'd been born a billion years earlier, you'd have inherited a larger universe, not a different one. The same galaxies, in the same places, with the line drawn farther out. Everyone who comes after us gets less than we did. Everyone before us had more. None of that is a prediction about technology. Faster ships don't help. Better engines don't help. Nothing anyone builds changes a single line of that schedule. The schedule is written into the geometry, and the geometry doesn't care what we do about it. Those departures are already booked.
And here's the part that makes none of it feel the way it should. Not one of them goes dark. If this stretch of the journey has unsettled you the way it unsettled me, take a second to like the video and subscribe. It helps this channel more than you'd guess. A galaxy crossing that boundary doesn't wink out. It doesn't fade to black and vanish from the plate. Nothing about the moment of crossing is visible at all, from either side. which is worth holding onto. There's no flash, there's no last frame. What happens instead is a freeze. As the galaxy approaches the line, its light keeps arriving, but the redshift climbs without limit. The light we are getting was emitted earlier and earlier in the galaxy's own history. Those emission times bunch up against a single instant, the one where it crossed. So the image stops advancing. We keep receiving that galaxy forever, and we keep receiving the same moment of it forever. At the same time, the photons come further apart.
Then further apart than that. The picture doesn't disappear. It thins out toward a limit it never quite reaches, over a stretch of time with no end attached to it. If that behavior sounds familiar, it should. It's what an object looks like falling into a black hole, watched from outside. The image slows, reddens, and stalls, and from the outside it never quite finishes falling. The physics isn't identical, but the geometry rhymes and the visual outcome is the same. The difference is which side we're standing on. With a black hole, the thing crosses and we stay. Here, we're the ones staying still, and it's the space that carries them over. Avi Loeb ran the numbers on this in 2002, and the result is precise enough to be uncomfortable. A galaxy we see today at a redshift of 5 to 10 has a ceiling on it. We will only ever see it up to an age of about 4 to 6 billion years in its own frame. 4 billion years is roughly the age of the Earth. So we get to watch those galaxies through the equivalent of one Earth lifetime of their history. And then the film ends. Not because they stop existing, because the rest of their story is emitted on the far side of a line, and it comes toward us, and it never lands. And the rule runs the way you'd least expect. The farther the galaxy, the younger it stays, permanently. The most distant things in our catalogs are frozen at the earliest moments. They will still be frozen there when the sun is a cinder. We will never see any distant galaxy as it is. Not tonight, not in a billion years, not ever. Only as it was. And the same thing is true in the other direction. From out there, we are the frozen picture. Say there's an astronomer on a world 30 billion light years away. She's looking at a smear of light from the Milky Way as it was long before the Earth had formed. That smear will stall too. She'll keep it forever, and she will never learn what happened here. There's a deeper problem buried in that, and it deserves to be named plainly. The word now has no meaning across those distances. There is no shared present moment between us and a galaxy at the edge of what we can see. Not in practice, and not in principle either, because nothing at all can pass between the two events to link them. What that galaxy is doing tonight isn't a fact we happen to lack. There's no way for it to exist for us at all. The expectation was that lost things disappear. The measurement is a photograph that never updates. You already know what that resembles. A picture of someone who left, taken at the door, and that's the only picture there will ever be. They keep going. They keep living. The frame doesn't move, and you can look at it as often as you like for the rest of your life, and it will always be the same afternoon. That's the relationship we have with 94% of what we can see. And while all of that is happening, something else is running in the opposite direction. The sky is getting fuller. There's light out there, emitted long ago by galaxies far past our current horizon that's still in flight and still inbound. It hasn't landed yet. It will. Objects nobody has ever detected are going to surface in our images for the first time and keep surfacing for a very long time. The far edge of that inbound mail sits at about 61 billion light years. Everything closer than that will eventually be seen. Everything past it, never. The volume between 46 and 61 billion light years works out to an extra 130% of everything currently visible. For every galaxy in tonight's sky, there are more than 2 more still in the post. So the eventual head count of visible galaxies is more than double what we have now. That should be good news, and it is in a narrow sense. There is more universe coming. Astronomy is not running out of material. Every one of those new arrivals is already past the line. Not marginally past it, wildly past it. They're farther out than the current edge of what we can see, which is itself more than twice the reach limit. They arrive as images and nothing else, permanently sealed, from the first instant we detect them.
They'll also be hard to catch. Light from that far out arrives badly stretched, dragged clean out of the range your eyes work in and down into the infrared. That's already why the newest deep sky telescopes are built as infrared machines rather than as bigger versions of the ones on hobbyist balconies. The frontier keeps sliding toward longer wavelengths, and the hardware has to chase it. So we're living in the richest era the sky has ever had in one narrow sense. And we'll hand the people after us a fuller catalog and a smaller estate. There's one more thing hidden in that 61 billion light-year figure, and it's the quietest fact of the night. It's a hard edge, not a limit of our instruments, not something a better telescope fixes. Past that distance, no light emitted at any time by anything will ever arrive here. And there is almost certainly more universe out there. Everything we can measure says the pattern keeps going, the same filaments, the same voids, the same galaxies, with no sign of a rim anywhere. It may go on without end. We will never see a single photon from any of it. Not us, not our instruments, not whatever comes after us. That part of reality is sealed, and it was sealed before anyone was here to notice. So the two curves run in opposite directions, and neither one is going to turn around. What we can see keeps growing. What we can touch keeps shrinking, more arriving, less attainable, forever. Picture an inbox that fills faster than you can read it, with letters from people whose addresses don't exist anymore. Those are the terms. So what does a civilization do when it works this out? Somebody has done the arithmetic, and it needs framing carefully.
What follows is a calculation about what physics permits. It is not a claim that anyone is doing it, here or anywhere else. In 2018, Dan Hooper published a paper with a straightforward premise. If the galaxies are living, stop chasing them. Bring the stars home instead. The method goes like this. You build a shell around a star and capture its light. Then you use that captured energy asymmetrically, pushing on the star itself so that it moves. Not fast. A star is heavy and the push is gentle, but you have billions of years. And you only need to move it inward toward the middle of your territory before the line sweeps past where it's sitting. It works best on the small, patient stars, somewhere between a fifth of the Sun's mass and about one solar mass. Those burn slowly enough to still be shining when they arrive. The big bright ones are useless. They die on the road. The reachable harvest, on Hooper's numbers, extends out to somewhere between 65 and 163 million light-years. That's a region roughly 30 times wider than everything gravity currently holds for us. The payoff is a several thousand-fold increase in the total energy a civilization would ever have access to. And there's a corollary harder to shake than the plan itself. If anyone out there is doing this, it should look like something. Stars behaving oddly, regions where the light is missing and the motions are wrong. It's a search we could actually run. Stuart Armstrong and Anders Sandberg went at the same problem from the other end in 2013. Their question was how far a single star system could spread if it built self-replicating probes and fired them outward. At half the speed of light, a few million galaxies. Push the probes closer to light speed and the number climbs into the hundreds of millions. Both papers spend most of their length on the unglamorous parts, which is how you can tell they're serious. Getting up to speed is the easy half. Stopping at the far end is the hard half. A probe that arrives at a galaxy at half the speed of light and can't slow down has accomplished nothing at all. And intergalactic space isn't empty. It's thin, but at those speeds, a single grain of dust is an explosion. So you don't send one probe anywhere. You send many copies of the same probe at every target. You accept that most of them are destroyed in transit. Then you plan the whole thing around whichever ones happen to survive. Now set that against what we can actually build. Voyager 1 is moving at about 38,000 miles an hour, which is roughly 70 times the cruising speed of an airliner. It has been doing that for 49 years without stopping. This November, it becomes the first object we've made to sit a full light day from Earth. Light crosses that gap in a day. Voyager needed half a century. At that speed, 1 light year takes about 17,000 years. Call it 700 generations of people, end to end, for a single light year.
The Parker Solar Probe is the fastest thing we've ever accelerated, hitting 430,000 miles an hour on its closest passes. That's 119 miles a second. In 1 second, it covers the distance most people drive in 2 hours. It's still a fraction of 1% of light speed. We've already met the one-gravity ship and the 100 years of shipboard time it would need. Nothing about the harvest plan is any easier. Every version of this requires a project that outlasts every institution that has ever existed on this planet by a factor no one can picture. So who decides? Who funds something that pays off in 100 million years? Who keeps it running after everyone who authorized it has been dead for 10,000 centuries? There aren't answers to that. There's barely a vocabulary for it. But the question underneath is simpler, and it's aimed at you. If the launch window is closing, and every year you wait costs you stars you will never get back, and you personally will never see any result whatsoever, ever, under any circumstances, would you launch it? Every number so far rests on one assumption, that we know where the line is. We don't. Not to the precision the story needs. The boundary is set by how fast the universe is expanding, and there are 2 good ways to measure that, and they disagree. The first route runs through the early universe. Take the microwave glow left over from the beginning and read the pattern of hot and cold spots in it. Feed that pattern into the model. Out comes a rate of about 67.4 kilometers per second per megaparsec. In miles, that's close to 42 miles a second for every 3.25 million light years. The second route climbs a ladder. Measure the distance to nearby parsing stars directly. Use those to calibrate brighter markers a little farther out. Use those to calibrate supernovae, which reach across the universe, rung by rung, out into the expansion. That route gives about 73.5. Earlier this year, a community-wide effort pinned the local number down to about 1%. It pooled telescopes and methods that had been arguing among themselves for a decade. The idea was to find the mistake. The gap got worse. Both camps claim an uncertainty of about 1%. The difference between them is around 9%. Those 2 statements cannot both be right, and everyone involved knows it. It's like watching 2 people weigh the same sack of flour. One reads 5 pounds, the other reads 5.5. And both of them can show you, convincingly, that their scale is good to a fraction of an ounce. This isn't new, and it isn't improving. The gap first surfaced as a mild inconsistency more than 10 years ago. It was small enough that most people assumed it would close as the measurements got sharper. Every sharpening since has widened it. And it can't be split down the middle. The 2 routes aren't measuring the same quantity with different amounts of sloppiness. One reads the universe as it was 380,000 years after the beginning. On that clock face, a fraction of a second past midnight. Then it works forward through the model. The other measures the expansion here, tonight, directly, without the model in the way. So if they disagree, there are only 2 options. Either one measurement is wrong in a way nobody has found, or something is missing from the model that sits between them. This is not a technical squabble. It lands square on tonight's topic. The reach boundary is calculated from the expansion rate. A faster expansion means a nearer boundary, which means a bigger loss. A slower one means the line sits farther out and we keep more. So when we say about 18 billion light-years, the word about is carrying real weight. Depending on which measurement you trust, the line sits somewhere between roughly 16 and 18 billion light-years. Which is exactly why the figure is about 94% and not a precise one. You can't even be told exactly how much has been taken. The size of the loss is itself an unfinished measurement. And in the last 2 years, the disagreement moved in a direction nobody had budgeted for. On a mountain in Arizona sits a 4-meter telescope with 5,000 robotic fibers mounted at its focus. Every 20 minutes, the entire array reconfigures itself. Each fiber swings to a new target and lands on it, accurate to about 1/10 the width of a human hair. Then it stares for 20 minutes and does it again, all night, for years. That instrument is DESI, and in April of this year, it finished the survey it was built to do. What it's really measuring is a ruler that got frozen into the universe at the very start. In the first few 100,000 years, before atoms existed, matter and light were locked together in a single hot fluid.
Pressure waves rang through that fluid, the way sound rings through air. Then the universe cooled enough for atoms to form, the fluid broke apart, and the waves stopped where they were. They left behind a faint preferred spacing, a slight tendency for clumps of matter to sit a certain distance from one another, printed across the whole sky and still there today. We know how long that ruler is, so every time Deci measures how long it looks at a given distance, it learns how much the universe stretched between then and now. Do that at enough distances, and the entire expansion history comes out, one slice at a time. 47 million galaxies and quasars. That's 6 times as many as every previous measurement of this kind combined. 11 billion years of expansion history mapped in 3 dimensions. The quasars are how it reaches the deep end. A quasar is a black hole at the center of a young galaxy. It's feeding, and it outshines everything around it put together.
Some of the ones in this survey sent their light about 11 billion years ago. That light doesn't arrive clean. On the way here, it passes through cloud after cloud of hydrogen, drifting between galaxies. Each cloud takes a small bite out of the spectrum at a slightly different wavelength. So the light shows up carrying a record of everything it went through, cloud by cloud, in order. Read the bytes and you get a map of the gas at distances no galaxy survey can reach. It's a single beam of light doing the work of a census. And because the machine has been performing better than anyone planned for, it isn't stopping. Observations run on into 2028. The result that matters tonight came out of the second data release in March of last year. 14 million redshifts. Taken by itself, the data is perfectly consistent with dark energy being a constant, exactly as the standard model has it. Combined with the microwave background, and with 3 separate independent collections of supernovae, it leans somewhere else. It leans toward dark energy that has been weakening over time. Sit with what that would mean. If dark energy weakens, the acceleration eases. If the acceleration eases, the line stops rushing inward. And if it weakens far enough, the line stops being a permanent barrier at all, and things currently written off come back into play. The 94% would not be a loss, it would be a lease. Now the counterweight, because there is one, and leaving it out would be dishonest. In January of this year, the Dark Energy Survey published its final analysis. 6 years of data pulled together through 4 different probes at once. It fits a constant. It also fits a weakening dark energy, but no better. From where that team is standing, there's nothing here that requires new physics. And in between those 2 results, the field had a genuine scare. In late 2025, a group argued that the acceleration itself might be an artifact. Their claim was that supernova in old galaxies are subtly different from supernova in young ones. Nobody, they said, had corrected for it properly. Put the correction in, and the expansion looked like it was slowing down. That would have taken out 1998, the Nobel Prize, and everything built on top of them. In June of this year, a team including 2 of the original laureates published the check. The earlier work had estimated the age gap between nearby and distant host galaxies at around 5.3 billion years. The real figure is closer to 1.9. They also found a standard correction had been left out entirely. Put both back in, and the acceleration is exactly where it always was. So that one held. The acceleration is real, and it survived the hardest hit anyone has aimed at it. But the thing it produces, the line itself, did not come out of that fight with the same clarity. As of tonight, nobody can tell you whether 94% is a permanent loss or a temporary one. One combination of the best data available says the line will keep closing forever. Another combination, from an equally careful team, says it won't move at all. The instrument built specifically to settle it has finished its planned survey and is still running. And in July of this year, a separate analysis put something else on the table. It argues that the universe may not be as smooth and as uniform in every direction as the entire calculation assumes. If that holds, the question isn't where the line sits, it's whether the line was ever computed on the correct foundations at all. Underneath all of those arguments sits the same hole, and it's the oldest one in the story. Nobody knows what dark energy is, not roughly, not in outline. There's a name for it, a measured strength, and a careful description of how it behaves. Past that, the file is empty. So let's go through the answers currently on the table. There are 5 worth your evening, and not one of them is comfortable. The first is the simplest, and it's the one most physicists would still bet on. There's a piece of history behind this one. In 1917, Einstein added a term to his equations by hand for the sole purpose of holding the universe still. He didn't like it. When the expansion turned up a decade later, he dropped it and reportedly called it a blunder. That term is exactly the term the acceleration needs. It sat unused for most of a century, an embarrassment in the textbooks. Then the supernovae came back dim, and it turned out to be the best fit anyone had. So the leading candidate is a piece of mathematics invented for the wrong reason and thrown away, then found to be right about a question nobody was asking. Empty space isn't empty. Quantum fields feel it, and those fields never sit perfectly still, so even a volume with nothing in it carries a base level of energy. Call it vacuum energy. It belongs to the space rather than to anything inside it. That's the property the acceleration needs. It fits the supernovae, the background radiation, and the clustering of galaxies all at once with one number. Then somebody tries to calculate what that number should be. The best motivated calculation comes out wrong by up to 120 orders of magnitude. Imagine estimating the price of a cup of coffee and coming back with a figure that has 120 zeros after it. That's the scale of the miss. It's the largest gap between theory and measurement anyone has ever produced, and nobody has found a way out. Attempts to cancel that enormous predicted value against something else tend to land at 0 or land at a number just as wrong. Getting it to come out small but not quite 0, and small by exactly the right astonishing factor? That has resisted every technique anyone has brought to it. So the leading explanation works perfectly, except at the one point where we try to say why. There's a second answer that doesn't require the vacuum to behave itself. Suppose there's a field spread through all of space, sitting on a very shallow slope and slowly rolling down it. Physicists call this quintessence. While it rolls slowly enough, its energy behaves almost exactly like a constant. Almost. Not quite. It drifts. That drift is attractive right now because drifting is what the combined data has been leaning toward. It also softens the question of why dark energy became dominant in this particular era rather than some other one. It's also testable, at least in principle. A constant gives the same answer at every distance. A rolling field doesn't, quite. Measure the push at enough different distances, precisely enough, and a drift should show up as a slope where a flat line ought to be. That's what the current surveys are hunting for. What it costs is a new field that nobody has ever detected in any other way. And the slope has to be absurdly gentle. Picture a hill so shallow that a marble takes billions of years to notice it's on a slope at all. That's the tuning required, and no known principle demands it. Maybe the answer is simpler than any of that. Maybe there's nothing pushing. Every one of these arguments assumes general relativity is correct across the whole universe. It's the most successful theory we have, and it passes every test we can run. But every one of those tests happens close to home, on scales unimaginably smaller than the ones in question. Perhaps gravity behaves differently across billions of light years, and what looks like a mysterious push is a familiar force getting the large-scale case wrong. The appeal is obvious. No new substance, no new field, just a correction to something we already have. The trouble is that relativity is stubbornly right everywhere we can check. And most attempts to bend it at the largest scales break something else, usually the growth of structure or the motions inside the solar system. People are still working on it. Nothing has stuck. There are live attempts. In May of this year, a mathematician argued that the acceleration could fall out of instabilities in the equations describing matter and gravity together. No dark energy required at all. That work is being argued over right now. It's early, and early is where most ideas in this area go to die. Now for the possibility that's hardest to sit with. Suppose dark energy has already changed once. If the leaning in the data is real, then this isn't a constant at all. It's something with a history, and anything with a history can have more of it. That doesn't just alter the forecast, it removes our ability to forecast. With a constant, we know precisely what happens next, forever, because a constant does nothing but continue.
With something dynamic, we know nothing until we know what drives it. It could strengthen and eventually pull apart the structures currently holding. It could weaken and coast. It could keep weakening past zero and start pulling everything back together. The confidence we had about the far future came entirely from the assumption that dark energy is boring. Take away the boredom and the future opens up in every direction at once, including directions nobody has modeled. And that leaves one more, which is the only one with a door in it. There's a single number that describes how hard dark energy pushes for a given amount of it. In the constant case, that number sits at -1. A calculation from 2005 worked out what happens if it ever climbs above -1/3. At that point, the acceleration stops, and the maximum distance a traveler could ever reach stops being a finite number. The horizon doesn't just slow down, it stops being a horizon.
This needs stating carefully because it's the kind of thing that gets quoted without its conditions. That result is a conditional. If the number moves, then the line opens. Nothing in the current data says the number is moving that far, and plenty of it says the number isn't moving at all. It's a possibility, not a finding, and treating it as anything else would be dishonest. But notice what it means that we have to say that. Which of these 5 is correct decides whether the sky above your roof tonight is a map or a museum, whether the things in it are destinations or exhibits behind glass. Notice one thing all 5 have in common. Not one of them was predicted. Every single one was written down after the measurement to account for the measurement. That isn't a scandal, and it happens in physics regularly, but it's worth being clear-eyed about. These are explanations built to fit a result, not results that confirmed an explanation. Nobody knows which one is right, and the answer may be a long time coming. But suppose it doesn't move. Suppose a constant really is a constant, and the standard picture is exactly right, and nothing surprising is waiting in the data. Then the schedule runs as written, and there's an endpoint to it. Within about 100 billion years, everything outside the local group has crossed the line. That's roughly 8 times as much time as has passed since the beginning of everything. Whatever is left of us at that point looks out at a universe containing one object. Our own group merged into a single thing. Andromeda and the Milky Way and Triangulum and the dozens of small galaxies around them. All of it folded together by gravity into one large elliptical blob of stars. The black holes from their centers spiraling toward each other somewhere in the middle. Everything else is on the far side, frozen, reddening and unreachable. And even that last island isn't settled. For a long time, the merger of the Milky Way and Andromeda was treated as a certainty. 4 or 5 billion years out, with a date attached and a name waiting for the result. Then, last year, a team took the best available measurements from Gaia and Hubble and did something the earlier work hadn't. They folded in every uncertainty they had, including the pool of the 2 largest satellite galaxies, and ran the whole thing 100,000 times. The odds came out at roughly a coin flip within the next 10 billion years. A direct head-on collision came in under 2%, and the first pass decides it. If the 2 galaxies swing by each other at more than about 500,000 light-years, they may drift on and never merge. So we don't know the internal arrangement of the one thing we get to keep. Either way, the rest of the group arrives eventually. The local group is bound, and bound things fall together. Over tens of billions of years, the small galaxies get pulled in, one at a time. What comes out the far end is a single elliptical, whatever the 2 big spirals do or don't do in the next 10 billion years. And inside it, the clock runs down. Gas is finite. Every generation of stars locks some of it up permanently, in dead cores and burnt cinders, and the supply of raw material thins. Star formation slows, then it stops. What's left burns for an extraordinarily long time. The small red stars, the dim ones nobody bothers to name, are stingy with their fuel. Some will still be going 1 trillion years from now, 10 times longer than the whole stretch of time we've been counting. The island doesn't go dark quickly. It just stops making anything new. None of it happens abruptly, and nobody living through it would notice. The change across a lifetime is nothing. The change across 1 billion years is total. A civilization out there would inherit a sky very slightly poorer than its parents' sky.
Then hand on one slightly poorer again. No single handoff would look like a loss. Now put yourself on a planet somewhere inside that island, 100 billion years from tonight. You have a sky. It has stars in it, plenty of them, low and red and burning slowly. It has whatever passes for a Milky Way by then, a band of them across the middle of the night. And past that band, nothing. Not darkness with faint things in it, not the way our darkness has faint things in it, if you know where to look and give your eyes a while to adjust. Nothing. No smudges, no islands, no second anything. Point the largest telescope you can build at the space between the stars and it stays empty. Every wavelength, every direction, however long you leave the shutter open. That's the sky, and it's stable, and it's all there is, and a second loss is coming, and it's worse than the first. Because the observers on that planet won't just lack the view, they lack the evidence. Follow it step by step. Everything we know about the expansion came from comparing distant galaxies with nearby ones. Farther away means more redshift, and that relationship is the entire foundation. Take away the external galaxies and there's nothing left to compare, no relationship to plot, no expansion to detect. You can't measure the stretching of space using objects that are all bolted to each other. Next, the background radiation, the oldest light there is. It's the glow left over from the moment the universe first turned transparent, and any decent antenna can pick it up tonight. It stretches along with everything else. Within about 100 billion years, its wavelength is up around a meter, roughly the length of a long stride. Its brightness has dropped by 12 orders of magnitude. That's 1 part in a trillion of what reaches us tonight. Worse, at that wavelength, it can no longer travel through the thin gas inside the galaxy. So even a perfect instrument, built by people who somehow knew to look, would find nothing. The signal doesn't just fade. It stops being able to arrive. Then the light elements, the hydrogen and helium forged in the first few minutes, carry a particular ratio. It matches the theory to remarkable precision, and it's one of the strongest pieces of evidence in the whole subject. But stars process gas. Generation after generation will run that original material through their cores and change it. Eventually, the primordial ratio lies buried under everything that happened afterward. And within roughly 1 trillion years, even the nearest loose protons drifting between galaxies have crossed the line. So here is what those astronomers will find. No expansion to measure, no background glow to detect, no untouched primordial gas to sample, no external galaxy to compare against anything, no redshift, no distance ladder, no history at all. They'll do everything right, they'll be careful and skeptical and rigorous, and they'll check each other's work the way we check ours. And they will conclude that they live in a single island of stars, eternal and unchanging. Around it, empty space going on forever, with nothing in it at all. Every observation they can make will support that conclusion. It will be the simplest explanation of all their data. It will be wrong about the origin of the universe, wrong about its age, wrong about what it's made of, wrong about where it's going. There is one way out for them, and it's fragile. They could be told. Somebody writes it down now. The writing survives. Every generation hands it forward with enough care that the reason for keeping it never gets lost. Then those observers would have a document, not evidence, a claim, from people who could still see. Consider what that asks. A record maintained without a break for 100 billion years. Every institution humans have built has lasted a few thousand at the very outside, and most of them nothing like that. The oldest writing anyone can still read is around 5,000 years old, and half of it is guesswork. And a document like that would be indistinguishable from the inside, from a myth. Careful people would be right to doubt it. Their instruments would say otherwise, and their instruments would be working perfectly. Which raises a question that won't go away. How would you know if you were the ones living late? Not in 100 billion years. Now, what has already left quietly before anyone was here to write it down?
What evidence expired during the 4 billion years before the Earth cooled? We assume we are seeing the full case. So would they. And there's already one place where the record was wiped. Whatever happened before the earliest moments anyone can model left almost no trace. And the leading account of that era says the erasing was thorough. That isn't 100 billion years ahead. That's behind us. That puts us in a very specific position. There's a coincidence at the center of modern cosmology that nobody has explained.
The density of matter falls constantly as the universe expands. The density of dark energy doesn't move. Two quantities behaving in completely different ways over billions of years, and right now they happen to be within shouting distance of each other. That's already odd. What makes it stranger is that this is the era with observers in it. And it's more than a curiosity about two numbers. It's a window, and four separate things are open at once inside it. We can still see distant galaxies. We can still measure the expansion by comparing them. We can still detect the background glow. We can still read the original ratio of the light elements in gas that hasn't been fully processed. Every one of those four has an expiration date. They don't expire together. They expire on a schedule, and all four of them happen to be readable tonight. Whether that's luck or selection or something we haven't thought of is an open question in its own right. People argue about it seriously, and there's no settled answer. One way of looking at it takes the mystery out. Observers need stars, and stars need heavy elements. And heavy elements need earlier generations of stars to forge them. That takes billions of years. Line up all the requirements, and the window for observers turns out to be narrow. And it sits roughly where dark energy takes over, which would mean nobody ever gets to be born early. Anyone who arrives near the transition, because that's the only stretch when arriving is possible. That argument satisfies some people and irritates others, and nobody has proposed a way to test it. One more coincidence sits on top of that one, and it's smaller and more awkward. The window in which the evidence is readable has been open for billions of years. The window in which anyone on this planet could read it opened about a century ago. What isn't in doubt is that the work is happening right now, in the window, while it's open. That instrument in Arizona keeps observing into 2028, well past the survey it was built to finish. On a mountain in Chile, a telescope with a 3.2 gigapixel camera started a 10-year survey on the 30th of June this year. To display one of its images at full detail, you'd need something like 400 television screens side by side. It photographs the whole southern sky over and over, and every night it issues around 7 million alerts about things that have changed. Nobody reads those by hand. At 1 a second, a single night's worth would take 80 days. What that camera is really measuring is shapes. Mass sitting along the line of sight bends the light passing it, so a galaxy behind a heavy clump comes out very slightly stretched. In any single galaxy, the effect is far too small to notice. Across billions of them, it maps where the matter is and how quickly it clumped together over cosmic time. That growth rate is a second independent handle on dark energy, and it leans on different assumptions than the distance measurements do. And at the end of this month, another telescope launches. Same mirror size as Hubble's, with a field of view 100 times wider. Where Hubble needs 100 separate pointings to cover a patch of sky, this one does it in a single exposure. Over its life, it expects to measure light from around 1 billion galaxies, and its main assignment is dark energy. It works differently again. It hunts exploding stars across a huge sweep of sky at once and measures galaxy positions in bulk. At a depth that would cost the older instruments decades. The assignment is built into the optics rather than bolted on afterward. So the answer to whether the line is permanent is not going to come from argument. It's coming out of hardware in the next several years, from 3 machines already switched on or about to be. None of the 3 is guaranteed to settle anything. It's entirely possible that all this data comes back, gets combined, and lands squarely in the middle. The constant and the rolling field both still standing. That outcome is more common than the press releases suggest. But this is the first time the question has been attacked at this scale, by instruments built for it rather than borrowed from other work. Which brings us to what's actually undecided, stated plainly. We don't know what dark energy is.
5 candidates, no verdict, and the leading one carries the worst prediction anyone has ever made. Settling that probably requires physics nobody has written down yet. We don't know whether it's constant. One combination of excellent data leans toward weakening. Another, from an equally careful team, sees no reason to abandon a constant. This one is answerable, and the answer is coming out of the surveys running tonight. We don't know exactly where the line sits.
The two best measurements of the expansion rate refuse to agree, and the line moves with them. Somebody will eventually find the mistake or find the new physics. 10 years of hunting hasn't turned up either. We don't know whether the smoothness the whole calculation assumes is a fair description of the universe at all. That's a live argument as of this summer. It's also the one that would hurt most, because it sits underneath everything else rather than beside it. And we don't know whether a reachability figure computed at light speed means anything at all. Our fastest machine does 119 miles a second. Light covers that same ground 1500 times over in the same second. The honest number for what a species like this one can reach isn't 6% of the sky. It's far smaller, and nobody has the first idea how to raise it. That's an uncomfortable list. It's longer than the same list would have been 10 years ago, which is not how this is supposed to work.
With all of that unsettled, here's what isn't. The expansion is real. It has been measured a dozen different ways by people trying to catch each other out. The acceleration is real. It took the hardest hit anyone has aimed at it in 28 years, and it came through unchanged. Dark energy is most of what exists. Whatever it turns out to be, it dominates the budget, and it has done so for billions of years. Structure is finished. Nothing larger than what's already here is going to assemble. That follows from the acceleration alone and doesn't depend on knowing the cause. Gravity still holds locally. Bound things stay bound, at every scale from an atom to a group of galaxies, and no amount of expansion touches them. There is a line. It's out there tonight, in every direction, at a distance we can state to within a couple of billion light years. Something is on the far side of it, not a boundary of the universe, not an edge.
More universe, full of galaxies that are ordinary in every respect, except that we can never go there. The light from that side still arrives. It arrived tonight. It will keep arriving for as long as anyone is here to collect it. And it will never once say what those galaxies are doing now, because there is no now to tell. And whatever the exact percentage turns out to be, and it isn't exactly 94, the shape of the answer doesn't change. Most of what we can see is not somewhere we can go. The light is still arriving. The galaxies are still shining. The line is still out there, still moving inward, still closing. We still can't cross it. And yet the light arrives. That's the part that keeps its balance against everything else tonight. Photons cross a gap that nothing can ever cross back over. They land on a mirror on a mountain. The mirror feeds a detector, and the detector feeds a number, and the number becomes a distance. Distances become a history. The history becomes a picture of how the universe is built and where it's going. And the thing holding that picture is a species that has been looking up for a few thousand years. One small planet, one ordinary star. Inside the small part of it we can reach. We mapped a place we can't enter. Nothing had to work out that way. It doesn't move the line, not 1 inch, not 1 mile. Understanding the geometry doesn't shorten a single journey or buy back a single galaxy, and it never will. The schedule runs exactly as it would have run if nobody had ever looked. Knowing costs the universe nothing and gains us nothing we can spend. But it does mean that what's living isn't living unrecorded. Someone was here and paying attention while it was still possible to see any of it. Thank you for joining me on this journey through the parts of the universe we'll never touch, and through the strange fact that we can describe them anyway.
If you'd like more nights like this one, subscribe and leave a like if this earned it.
It's a small thing, and it helps. The next time you're outside under a clear sky, remember that a beam fired straight up tonight would never land on almost anything up there. Then find that faint gray smudge between Andromeda and Cassiopeia and take a moment with it, because that one is still ours. Good night, and may everything you reach for stay inside the line.